Hello everyone, welcome to our discussion of section 8.4 where we will be talking about more convergence tests. Now in section 8.3 we talked about the integral test, the p-series and the comparison test, and the limit comparison test as you can see on the screen. But all these tests apply to series that have only positive terms. In this section, we will discuss more convergence tests such that they can apply to series that they do not necessarily have positive terms. They can have negative terms as well as positive terms. These are their names shown in red, the alternating series test, the ratio test, and the root test. Now, if you have any series that have if you have alternating series tests or alternating series, that is series that have both positive and negative terms, if you consider just the positive terms, which we will in some cases in this section, so if you consider just the positive terms in the series, we can apply these tests that we discussed in section 8.3. Okay, so that is also possible. So here they are, the ratio test, the root test, and the alternating series test. We will also talk about the alternating series estimation theorem. So this theorem tells us how many terms in an alternating series we need to add in order to meet a certain accuracy for the series. Remember, series is just the sum of the terms in a sequence. Now, when we have infinite series, that is a sequence with infinite number of terms in it, if we sum the terms, if you want to find the sum of a convergent series, then we're still approximating, right? Because we have infinitely many terms and we're summing, it's impossible to add infinitely many terms. So even though we have methods for summing infinite series, it's still an approximation. So we want to, on occasion, determine what is the accuracy of adding certain number of terms, or how many terms should we add in an infinite series in order to achieve a certain accuracy. And this theorem is good for establishing that. It will tell us how many terms in an infinite series we need to add. More specifically, it should be an alternating series. How many terms in an alternating series must be added in order to achieve a certain level of desired accuracy? We will look at examples of that too. Also, we will look at absolute convergence. And here we may apply any of the tests that apply to series with positive terms here. And because we're looking at just positive terms in a series, that's why we can also apply the methods we learned in section 8.3, the integral test, the p-series and the comparison test, and the limit comparison test. Now we will also look at conditionally convergent series. So these are, just to briefly mention what they are, these are series that are convergent, but not absolutely convergent. In other words, if you consider, for conditionally convergent series, if you look at just the positive terms, they do not converge. But if you look at the negative and the positive terms together and you take the sum, take the series that way, then they will converge. So in situations like that, we will say the series are convergent, but not absolutely convergent. Okay. Having said that, then let's look at an example of alternating series. So alternating series are series where the terms have alternating algebraic signs. So positive, negative, positive, negative, positive, and so on. Or you can have negative, positive, and so on. But if we have positive and then negative, 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 and then another positive, and then another negative, then that's not an alternating series. It should be that each term has a different algebraic sign than the one previous to it. And that's an alternating series. And this is an example. If you are given an alternating series in this form, you will have to find the general formula for it before you can determine whether it is convergent or divergent. So if we are given a series in this form, we will have to find this form for it, the general term of the series for it, before we can look at whether this series converges or diverges. Okay. So, what is the alternating series test then? It has, simply put, it has two conditions, condition 1 and condition 2. So given an alternating series, the alternating series converges if it satisfies these two conditions. Condition 1 says that each next term, that is bn plus 1, and with bn's, these are all the positive terms, not the negative ones. All the positive terms should be, all the positive terms that are coming next should be less than or equal to the term, the positive term that comes before them. This should be always true for any two positive terms that we find in an alternating series. Oftentimes, alternating series are written specifically in this form, -1 to some power, in this case n minus 1. But it could be, which applies to this of course, if n equals 1, we get power will be 0, -1 to 0 power is just 1, and it's just positive. So you can see the first term is positive. If n is 2, then we get -1 to first power or power 1, which means the minus is preserved, so the second term is negative. But if we have the factor that affects the algebraic sign in the series written in this form, specifically in order to make sure that we know the part of the series that gives us just the positive terms, or just the terms in absolute value form. And writing a series in this form is useful for that very reason. Right away, we know that bn's are always greater than 0. Okay, this is to just give the series in a way that shows us that part of the series that is positive immediately. So the part of the series that affects the change in the algebraic sign is always written in this form, and that's for that reason. Okay, because we will have use for what bn is. Quite often we need to know what bn is. So if bn plus 1, every next positive term is always less than or equal to the positive term before it, then that means that the sequence for which we're obtaining the sum is a decreasing sequence. So this is a decreasing series. If that condition is satisfied, and if we take the limit of the positive terms, or bn's in the series, and we end up with 0, then the alternating series is convergent. So these are the two conditions that are necessary for any alternating series to be convergent. Okay, just these two conditions. The series has to be a decreasing series, and the limit of the bn's, that is just the terms without the algebraic sign. The limit of the terms without the algebraic sign should be equal to 0. Okay, so let us look at an example to see how all of this tests and theorems and definitions actually work. So here is one example of what I just said, that if you are trying to establish whether a series is convergent or divergent, if it's been given to you in this form, you will need to write it in this form, okay, before you can see whether it converges or diverges. This is one example, okay? So we need to find the general term for this series. So that is the first thing we need to establish. The general term for the series. Okay, so let's see how we can do that. The numerators are constants, right? So that's easy to establish. It's just going to be 4. Obviously, we are positive, negative, positive, negative. So this is an alternating series. And when we start from positive and then negative, in that example, we know that we can obtain that by saying -1 to n-1 power. So we can easily establish that. Let me write that. I'll write it here. So note that for this alternating series, if we have -1 to n-1, we'll obtain the correct algebraic sign for each term. For each term. Okay, so we have that. We also know the numerators. Now we have to find how to generalize the denominator term. So this is the first term, right? This is, so this would be n equals 1. So for n equals 1, we have that term. For n equals 2, we have this. This is n equals 3. Maybe I should put actually an arrow here rather than an equality. Okay, so like that. So this is n equals 3 and so on. N equals 3, and that is n equals 4. Now, when n equals 1, the denominator is 7. So that's 6 more than the position for this term, 6 plus 1. When n equals 2, the denominator is 8, so 6 plus 2, 8. When n equals 3, the denominator is 9, so 6 plus 3 is 9. It looks like if we add 6 to the n, to the position of each term, we will get the denominator. So 6, this would be n equals 5, right? N equals 5, so 6 plus 5 is 11. So let's also write that down, that the denominators can be obtained using n plus 6. Using, and I think I can write it in this corner, n plus 6. Okay, so then we have everything we need to write a general term for this series. Is this. So we have n equals 1 to infinity. We said that we can model the algebraic sign or the correct algebraic sign for each term with this. So -1 to n-1. And then our bn's are going to be 4, right? So 4 divided by n plus 6. So this is the general term for the series we have. Now that we have this, we can talk about whether this series converges or diverges. And because it's an alternating series, we will apply the alternating series test. Remember that the alternating series test had two conditions that we have to look at, right? One is we have to make sure that this is a decreasing series. That is, each next term is less than or equal to the previous term. Then, if we take the limit of the bn's, we have to end up with 0. If we satisfy these two, we have a convergent alternating series. So let's check each condition. So we have checking condition 1. Series test. So we can see that for increasing values of n, this bn, so note that bn's are equal to 4 divided by n plus 6, right? These are the bn's. This will create or give us the alternating algebraic signs. So if you look at the bn's, which are captured in this ratio, for every n increasing n value, which starts from 1 all the way to infinity, this fraction becomes smaller and smaller and smaller, right? So in fact, bn plus, so given, let me just say given that bn's are that, therefore, we can see clearly that bn plus 1 will have to be less than or equal to bn's. Okay? In fact, it will never be equal to bn. It will always be less than bn. Okay? Therefore, this is a decreasing series. Decreasing series. So it satisfies condition 1. So condition 1 is satisfied. Oops, let me move this up. Is satisfied. Next, we will have to check condition 2 of the alternating series test. And since this is the first example, I'm writing them out, but next I won't be as detailed as this. So checking condition 2 of the alternating series test. So that's when we take the limit of this, and if it's equal to 0, then condition 2 is satisfied, right? So let's do that. Once again, given that our bn's are equal to 4 over n plus 6, then we have limit of the bn's as n goes to infinity equals limit as n goes to infinity of 4 divided by n plus 6. It's clear that if you plug in infinity here, this whole ratio will go to 0, right? Like that. So condition 2 is also satisfied. Okay, so by the alternating series test, this series is convergent. convergent. Okay. Not always it's so quickly we can establish whether the limit is equal to, or whether the function is decreasing or increasing. Sometimes we will have to, and you'll see examples of this coming up, we will have to take the first derivative test in order to establish whether the bn's are decreasing or increasing. In other words, we will treat the bn, this ratio or quantity that represents bn, as a function. And then we will take the first derivative of it, and we learned how to do that in Calculus 1, and we will look at if where the first derivative is negative. And in all those regions, the original function has to be decreasing. Okay, sometimes we have to do that. It's not always as quick and as easy as that for condition 1. Okay, so let's look at another example. In fact, this is one such example where we will have to look at the first derivative. Okay. So once again, we're asked, looking at this, we can tell that this is an alternating series. So applying the alternating series test is a good choice for us to determine whether this converges or not. Okay. So let us begin to check the conditions. Probably it's a good idea if you pause the video and take maybe 20 minutes, work on this, and then once you're done, check back with the video and see how our solutions agree. So I highly encourage that. So note that this quantity is always positive, right? So this is our bn's. So we have the bn's are equal to n divided by absolute value of n cubed plus 2, right? Just looking at that, we can establish that very quickly for all n. All n meaning from 1 to infinity, right there. Okay. Now, to check whether this is a decreasing or increasing function, let us turn this into a function of x and take the first derivative. So let me write that down. To find whether bn equals n over square root of n cubed plus 2, a decreasing or increasing function so let us write it as a function of x and conduct a first derivative test. Okay, so let's do that. So that is then, we will write f of x is equal to x divided by square root of x cubed plus 2. Keep in mind that even though we're writing it in this x form, x, the domain of x, is for n, it's going to be the same as domain of n, right? The same as n. N varies from 1 all the way to infinity, positive infinity. So the same is true here. Okay, so, and let me also add that for x greater than or equal to 1. I just wanted to make that clear. Now, let us rewrite this in terms of a rational exponent of the denominator and then take its derivative. So f of x can be written as x over x cubed plus 2 to 1/2 power, and therefore f prime of x, so we're taking the derivative, so 1 times all of this minus, so we learned this in calculus 1, right? So, and then derivative of this times that, so 1/2 times x cubed plus 2 to minus 1/2 power, and then times x, of course, but by the chain rule, we have to multiply this by 3x squared, right? So 3x squared, so that is the derivative of the denominator times the term in the numerator. All of that divided by this, all of this squared. So we have x cubed plus, sorry, let me move this up, x cubed plus 2 to 1/2 power squared. Okay. All right, so as you can see, we have plenty of simplifications to do. So let's do that. We have that. So we have x cubed plus 2 to 1/2 power, and then minus 1/2. So we have minus 1/2, and then 3x cubed there, right? So minus 1/2 times 3x cubed times all of that, x cubed plus 2 to minus 1/2 power. And of course, let's simplify this. So 1/2 power, distribute the 2 into this. We just get the powers cancel each other out. We just get x cubed plus 2. Okay. Now there's more we can do, right? We can then factor out, for sure we can, because the inside of the parentheses is identical, we can factor out the term with the smallest exponent. And then also, it's customary to also factor out any fractions like that. So we want to factor out even 1/2 as well. And then we will put a 2 here to balance the 1/2 that we're factoring. So that'll 1/2 times 2, we get positive 1 back for the first term here. Okay, so let's do that. So f prime of x is equal to 1/2 times x cubed plus 2 to minus 1/2 power, factored out, times, so to obtain this, we will have to have a 2 times 1/2, we get 1 back. And of course, we have to have a positive 1/2 power, not a negative. So that means we have to have a x cubed plus 2 here. So power here is 1. We'll add to this. We get positive 1/2 back. Okay, so that's that. And then also the rest of this, so we have minus, and then 3x cubed is the only thing missing from this bunch. Right, so minus 3x cubed, like that, divided by the denominator. We have x cubed plus 2. Okay, so now there's a lot of things we can do here. Right now we have a complex fraction. Because this 1/2 is distributing itself to everything here, so this 2 belongs to, is a denominator to this whole thing, which means it'll make this a complex fraction. We definitely want to simplify that. And 2 times this, to simplify it will be simply 2 times this. And then also this negative power we can combine it, we can bring this whole thing to the denominator, combine the 1/2 with 1 power here, we get 3/2, and then 2 also will be part of this. So there's a lot we can do to simplify, and let's do that. So I'm going to move the 2 and this to the denominator. So in the numerator we will have just this, and then we'll have to distribute this and combine the terms. Let's do it step by step. So we have the first derivative. So we're doing all of this so that once this expression is simplified to the extent possible, then we can work out where the original function is decreasing or increasing. Okay, so we will have that 2 times x cubed plus 2 minus 3x cubed divided by, so 2 times x cubed plus 2. Power of this is 1, power of that is minus 1/2, but when you bring this down to the denominator, it'll be positive 1/2. Plus this, we will get 3/2 as a power, right? Positive 1/2. When you bring it down, it'll be positive 1/2. Plus 1 is 3/2. Okay, is there anything else we can do to simplify this? Yes. Look at the numerator. We still have things to distribute and simplify. So we have 2x cubed, let's distribute this, plus 4 minus 3x cubed divided by all of this, 3/2, right? Of course, we can combine these two. We will get 4 minus x cubed. X cubed divided by all of this. Okay, so now we have this expression simplified as much as possible. So when is this? Because we know that this is always positive, especially for x values. Remember that for x greater than or equal to 1, this denominator is always positive. So this first derivative, it can only be negative if for some occasion the numerator is negative. So let's find out when the numerator is negative. So f prime x is less than 0 only if 4 minus x cubed is less than 0, right? If that's negative, the first derivative is negative. So let's solve for x using this. So we have x cubed greater than 4, and therefore take the the third root of both sides. So we will have x greater than third root of 4, right? When we take the third root of both sides, this is what we end up with. And by the way, this is let me approximate this. Third root of 4 is roughly 1.6. Okay, so given the fact that x is mimicking n, and n is, in this case, is just positive integers starting from 1, 2, 3, and so on, so we can establish that for n values that are 2 and larger, because we can have 1.6 for n, right? We're talking about x is mimicking the value of n, which starts from 1 and goes to infinity. So the next value of x that we need to obtain in order to ensure that this is the first derivative is negative would be 2. So then let me write, so for those values, well, I'll write it down. note that because x is mimicking n, right? So for n greater than or equal to 2, the bn's are decreasing. Then bn, which was equal to, it was equal to, what was it equal to? It was equal to that, right? N over a square root of n cubed plus 2. Oh, my ink is running out there. Oops. So n cubed plus 2 is going to be less than 0. Less than 0, therefore, thus bn plus 1 is going to be always less than bn for n greater than or equal to 2. Okay? So this satisfies condition 1 of the alternating series test for n values equal to or larger than 2. So let me condition 1 is satisfied. Okay? So now, so the function is, or the bn's are decreasing for n values greater than or equal to 2, which is good enough for us. Now, condition 2 to check condition 2, we have, let's find the limits. The limit of this as it approaches, as n goes to 0. So limit of bn's as n goes to infinity equals to limit of n over square root of n cubed plus 2 as n goes to infinity. So to find the limit in this case, we will divide all the terms in the numerator and the denominator by the highest, by the n term with the highest power in the denominator. And in that case, it's n to 3/2 power, or we can just look at it as square root of n cubed. It makes no difference. Either square root of n cubed or n to 3/2 power is the highest power of n in the denominator. So let's do that. Let's divide everything by that. Limit as n goes to infinity, n divided by square root of n cubed divided by, same thing in the denominator, n cubed divided by n cubed, all of it under the square root, plus 2 divided by n cubed, right? So what do we get? We get let's simplify. So we get, this is just, I will include that step as well. So this, if we simplify this, what do we get in this one? We get n divided by n times a square root of n, right? And then here we will get 1 plus 2 times, 2 divided by n cubed, right? Now apply the limit. Well, before that, we should simplify this, right? Because these two cancel out. So let me put another step here. I will just write it here. Limit of 1 over square root of n, of course, as n goes to infinity, divided by square root of 1 plus 2 over n cubed. So just apply the limit as n goes to infinity. That will be 0, right? We will have 0 divided by square root of 1 plus 0, and this is of course 0. Okay, so the condition 2 is satisfied as well. Is satisfied. Okay. All right, so we have both conditions of the alternating series test satisfied. So the series, this is our conclusion. Is convergent. By the alternating series test. Okay, so like that. Okay, I hope this matches the work that you did on your own scratch paper. And if not, I trust that you will let me know if you have any questions about this. So here is the alternating series estimation theorem. So when we have an alternating series, sometimes we are asked to add as many terms from the series as it would meet a certain accuracy for approximating the sum of the series. Okay, in that case, we can apply this estimation theorem, which helps us figure out which terms or how many terms we should add to achieve a certain accuracy for the sum. Okay. So this is just saying that if you have an alternating series that converges according to the alternating series test, so we've already established that the series is convergent. If it's divergent, forget it. We're not going to apply this. But if it's convergent, then we know that these two conditions are already satisfied, right? In such cases, when we have a convergent alternating series, then we can find the error in approximation of an infinite series due to adding terms from an infinite series. So the error, we can find it using this inequality. So the error in adding a certain finite terms from an infinite alternating series, a convergent infinite alternating series, can be found by looking at the positive terms evaluated for a certain n. And we will do one or two examples so you know exactly how this works. But bn plus 1s, so this left side represents the error in adding the terms, right? But that error is always less than or equal to bn's if bn plus 1 represents the maximum error of adding b1 to bn terms. This is very important. Please make sure you understand specifically what this side is saying, or this whole thing is saying. So this left side, I've tried to explain it here, but it just represents the error that we inevitably have if we try to approximate an infinite series with finite number of terms from it, right? So inevitably we will have error. That's all that is saying. It's saying that that error is less than or equal to a certain value of bn's such that if we add b1 through bn before that, we will get an error that is less than or equal to that amount. I mean, this is harder to describe than actually do in practice. That's why we will look at, I can't wait until we get to the examples. So here's an interpretation. I've tried to interpret that in this paragraph. So interpretation of this, what we have in this box, is this. For example, if error is that, this is the desired error, right? Suppose we're asked to add a certain finite number of terms from a convergent, infinite, alternating series such that the error is less than 0.0001. Okay? How do we establish that? I mean, how do we ensure that the error for the terms we're adding is less than that? Well, suppose that we calculate B6. That is the sixth term in the series. We calculate it, and this is the value we get. And remember, this is a convergent alternating series. We've already established that. And we calculate B6, and we get that. Notice this has 4 zeros after the decimal point. This is 3. So this is certainly smaller than that. And it occurs when? It occurs when we calculate the sixth term in the series. Then that means adding B1 through B5 will have an error less than 0.001. Okay, so if you calculate a certain Bn and you get a value that is less than that, it's telling you how many terms before that you can add such that the maximum error is that, which is much, much less than that error that we have been asked to have in our adding of the terms in this series. So once again, if you have for a certain Bn, in this case I'm giving an example that this is B6, but this Bn can be anything. It could be B4, it could be B8. In this case, B6, you have this value that you can calculate. Notice that this is much smaller than that. What this is saying, it's saying that exclude the sixth term. For the first 5 terms, if you add them, the error that you have, it's going to be maximum this much. Much less than that. Okay, so if you add the first 5 terms, you will satisfy the error condition that was set for you before you started adding the terms in the series. Okay, so if a certain Bn gives you a value that is less than the error, then you want to add the terms before that to achieve that level of error. So every Bn plus 1, in other words, every Bn plus 1 gives us the error for adding B1 through Bn, excluding Bn plus 1. Let me repeat that. Every Bn plus 1 gives us the error amount, maximum error, for adding B1 through Bn. Okay, so this Bn plus 1 is telling us how much error do we have if we add B1 through Bn. Okay, so let us see a couple of examples then. So show that the series is convergent. That's what we have to do before we look at the error condition. If it's divergent, we don't even worry about this. First thing, we should show that the series is convergent, and then how many terms of the series do we need to add in order to find the sum to the indicated accuracy? This is the indicated accuracy. The error should be less than 0.0001. Okay? So let us first show that this alternating series is convergent. We have to show that those two conditions are satisfied, right? So let's do that. And it's probably a good idea if you pause the video at this point and show that this series is convergent. Okay, so note that the Bn for this alternating series, Bn's are equal to 1 over n times 5 to the n power, right? Exclude that from the Bn's. Just a quick look, you can see that because n varies from 1 to infinity, then for every increasing value of n, this will decrease, become smaller and smaller and smaller. So for sure, Bn's from this, because this is our Bn, then Bn plus 1s will always be less than or equal to Bn. So condition 1 is satisfied here. Okay. Condition 1 is satisfied. Okay, that's one thing. So condition 2 is where the terms are decreasing. That's what this is saying. The terms are guaranteed to be decreasing. Now we have to take the limit of this. And show that it's equal to 0. So note that limit as n goes to infinity of the Bn's is equal to limit as n goes to infinity 1 over n times 5 to the n. And for sure, as n goes to infinity here, this Bn's are equal 0. Okay? So we know that condition 2 is satisfied. Okay. All right. So now that we know, well, let me actually conclude that. So our series is convergent. Alternating series test. Okay. Now, to determine the number of terms that we need to add, so the other part, right? How many terms of the series do we need to add in order to find the sum to the indicated accuracy, to this accuracy? Okay. So, to determine the number of terms to add to achieve this accuracy, okay, let's just start with n equals 3, because it wouldn't make sense if you start with n equals 2, right? Because even if n equals 2 is less than this, then how many terms do you want to add? Just one term? Because that will tell you how many terms before that you can add. So I would start with n equals 3. I would never start with n equals 2. Minimum, I would start with n equals 3. So if n equals 3, then B3, or our BNs, right? These are our BNs. Right there, let me actually, if I can find my highlighter. So these are our BNs, right? So I'm going to plug in for n here with 3. So so for n equals 3, then B3 would be equal to 1 over 3 times 5, 5 times, 3 times 5 cubed. That's what we will have here. And this will be equal to point, and please verify these numbers on your own, but this is what I got. This is what I got. Is this larger than that or smaller than that? For sure, this is larger than that, right? So if you add the first two terms, we're not going to add the third term. This is just saying how many terms before n equals 3 you can add to achieve this accuracy. So if you add the first two terms, you're going to have this much error, which is larger than what we're asked to achieve. So we can't stop with two terms. Let's try if n equals 4. So if n equals 4, then B4 is 1 over 4 times 5 to 4th power. Right? You can still see it here. Disregard the minus 1 to n power because we're just looking at BNs. So then the error that I got, or the value I got, is 0.004, which is still, so this is greater than, for n equals 3, we got a value that is greater than that. So we can't stop there. So this is still larger than that, right? 0.0001. What it means that if you add the first 3 terms in the series, you will get an error that is larger than what is requested. So we can suffice with adding the first 3 terms. Let's add, or let's find what happens for n equals 5. Okay, so if n equals 5, then we have 1 over 5 times 5 to 5th power, all 5s, right? Then what we will get is, let's see, I'm just double checking to make sure. Yes, that should be okay. So this is the number I got, 0.000064. And notice this is much less than the error we were asked. So this is less than 0.0001. Okay? So because of that, because this B5 gave us an error, gave us a value that is less than the error we're set. So this is telling us, by the alternating series estimation theorem, we know that if we add the first 4 terms, B1, B2, B3, B4, we will have an error that is much less than that. Okay? In fact, the maximum error would be that much. Maximum error, so which is much less than the standard we were asked to meet for the accuracy of adding the terms. So this is good enough. So because of this, then we can say that to achieve this error that we were asked to achieve this, the first 4 terms, right? This is B5 gave us this error, which was less than that. So that means 4 terms, the terms before it should be added, not this one. The terms before it should be added. The first 4 terms, we must add the first 4 terms to achieve the desired error. In other words, I want to make sure that this is clear. The first 4 terms would be B1 plus B2 plus B3 plus B4. Okay, that's what it means. Okay, let's do another example of this kind. It's going to be a little bit different, but pretty much in the same context. Here we're asked to approximate the sum of the series correct to 4 decimal places. Okay, so we just want to know when we should stop. Okay, that's what we need to do. Okay, so let's add the first 2 terms, right? For n equals 1 and n equals 2. In fact, why don't you pause the video and see how far you will get with this. Okay, that would be great to do. Okay, so I'll begin with the sum of the first 2 terms, or S2. So when n equals 1, we will get minus 1 over 2 factorial, or 2. And then plus, when n equals 2, we get minus 1 squared, which is positive 1, over 4 factorial, which is 24. So if we add these 2 terms, we will get minus 0.5 plus. These are my numbers. Please don't trust them. Come up with your own numbers and see if you agree with these or not. And if there's an error, let me know, please. I will correct the video content. Minus 0.4, minus 0.45, 8, 3, 3, 3. So that's what I have. Okay, so let's find the sum of the first 3 terms. That would be S3, which includes this sum. So I'm just going to grab that number. And I'm going to the next one. When n equals 3, this minus stays, right? Minus 1 cubed, we will have minus 1 over 720. That would be 6 factorial. So 6 factorial, when n equals 3, we will have 6 factorial, which is 720. And then what I ended up getting is minus 0.459722. Okay, so there is it's clear that right now our 4 decimal places do not agree, right? These are if you just look at the first 4 decimal places. So this is saying find the sum of the series correct to 4 decimal places. They definitely do not agree. So we need to continue. Let's continue. So I will find the sum of the first 4 terms, right? S4, which means I need that. That tells us the sum of the first three terms. So minus 0.459722. And for n equals 4, this minus will drop out. We will get 1 plus, and then plus 1 divided by, this will be 2 times 4 factorial, or 8 factorial, which is 403 40,320. That's 8 factorial. Okay, coming from there. Okay, so if we then add this to that, this is what I got. I got minus 0.459697. Something interesting happens here, because if you compare this with that, see, the fourth decimal place, everything is the same except the fourth decimal place. But if you look at the fifth decimal place here, which is 9, then this can easily be rounded up to give us that. So this is almost, so this is, let me just say, almost that. After rounding the fourth decimal place, we get minus 0.4597. Okay, so it looks like we found the accuracy, how many terms we should add to obtain an accuracy to up to 4 decimal place, because this is very, very close to that. I mean, 9 after 6, you can easily round this to that and you get the same value. So we found the accuracy we'd like. And also note, that this piece, just this piece, 1 over, so B4, right? This is the sum of the first 4 terms. But if we just look at this term, which is B4, which is equal to 1 over 40,320, what do we get? We get, roughly, we get 0.000025. Look at that. So you have 4 zeros after the decimal place, which means adding this to the previous value isn't going to change the fourth value that much, the fourth decimal value that much. So this is correct. So we can, based on what we have in front of us, we can conclude, so I will write that out. Notice that B4, this quantity, if we add B4 to S3, the sum of the first 3 terms, will not change. The fourth decimal place will not change because of the rounding, right? Just so we can easily bump this up to 7, having a 9 after it. So thus, by the alternating series estimation theorem, estimation theorem, the sum of the series if the series is correct to 4 decimal places, not if, but is Well, if we add the first three terms. So that is S3, which is B1 plus B2 plus B3, which is equal to minus 0.4597 after rounding. Okay, like that. All right, I hope this is making sense of what alternating series estimation theorem says. Okay, so next we will look at absolute convergence and conditionally convergent series. So absolute convergence is when we have a series such that the absolute value of the terms is convergent. In other words, you can have an alternating series, but if you take the absolute value of the terms, and if it's convergent, then that is called that the series is absolutely convergent. By the way, absolutely convergent series, that means it is convergent in any case. Okay? If it's absolutely convergent, then for sure, if you include the negative and positive terms, not just the absolute value of the terms, it will also be convergent. So absolute convergence is a strong status for series being convergent. It's a strong convergence. Okay. Now, the conditionally convergent case is when we have series that are convergent but not absolutely convergent. In other words, if you include the positive and negative terms in the alternating series, if you add all the terms, positive and negative, this series is convergent. But if you take the absolute value of the terms and then look at the convergence, the series does not converge. So when the series is convergent with all its terms included, but if you take the absolute value of the terms and then it's divergent, then we call such series, alternating series, conditionally convergent. So simply put, conditionally convergent series are series such that they converge, but not absolutely convergent. Okay? And here, as you can see, one example. We know that the harmonic series diverges. Not the alternating harmonic series, but the harmonic series, which is all the terms that are positive, right? Harmonic series with all the terms positive diverges, but the alternating harmonic series, the one that has positive, negative, converges. So the alternating harmonic series is a good example of a conditionally convergent series. It converges if you include positive, negative terms all at the same time. It converges. But if you take the absolute value of these terms, it becomes harmonic series, and we know that harmonic series diverges. And there's a nice proof in your book about that. Okay. All right. So having said that, let us look at some examples of this. So it says, determine whether the series is absolutely convergent, conditionally convergent, or divergent. Okay. All right. So Notice that this is an alternating series, right? So let's, and this is our BNs. Okay, note that, by the way, this is the solution, starts here. So note that Bn is equal to n over n squared plus 4. Okay. Notice that for n values, 1 to infinity, this is always greater than 0, right? So this is always positive. So just mentioning that this is Bn is enough, is sufficient that we say that this is always positive or greater than 0. Okay, for n greater than or equal to 1. Now, we need to then, applying the alternating series test, we need to show that this is decreasing, right? Or whether it satisfies condition 1 or not. So to show is satisfying condition 1, let's form a function with x being 1 or greater, or x from 1 to infinity. So f of x equals, I'm going to replace n's with x, divided by x squared plus 4 for x greater than or equal to 1. Okay. Let us then take the first derivative. We want to show that this function, or where this function is decreasing and where it's increasing. F prime of x would be 1 times x squared plus 4 minus 2x times x divided by, of course, all of that squared. Okay, so we have f, or the first derivative equals x squared plus 4 minus 2x squared, right? So we have, so if we simplify all of this at once, minus 2x squared plus x squared, we get minus x squared plus 4, right? We have that divided by x squared plus 4 squared. Okay, so the denominator, oops, sorry, I was off the screen. I apologize for that. So the denominator is always positive, right? It's squared. But so this first derivative, it's going to be negative whenever this numerator is negative, right? So let's solve this for 0. So to find the threshold value. So so if minus x squared plus 4 is less than 0, right? So then, so if that's negative, when would it be negative? It will be x squared greater than x squared greater than 4, which means x greater than, so greater than negative 2 and less than, well, let's see. So we have x greater than, let's see, x. So we have greater than, taking the square root of both sides. So we have absolute value of x. Well, this is, so x squared less than 2. Well, greater than, so this is, would be, I'm just double checking this, so x greater than 2, right, and x less than negative 2. So if x is, or x less than negative 2, right? For these two conditions, this numerator will be negative 2. So, I mean, for these two conditions, the first derivative will be negative. Now, this we cannot accept, right? Because remember, x is mimicking n, and x has to be either 1 or greater than 1. So this is out of the question. So this is out of the question. And we can just say that this is the acceptable one. So for n equal, therefore, so because of that, thus for n greater than 2, we can say that the bn's are decreasing. Bn plus 1 will always be less than bn. Okay, so the first derivative helped us establish that. And so satisfying condition 1. So satisfying condition 1. Okay. All right, so now we also have to look at the limit of the bn's and see if it equals to 0. So let me do that. So I actually better move to the next page. I don't want to clutter this page too much. So to check condition 2, we take the limit of bn's as n goes to infinity, and this is limit as n goes to infinity of n, these are our bn's, n over n squared plus 4. Okay. So we can easily find the limit of this. Let's divide all the terms here by the highest power of n in the denominator, which is n squared. So we have n divided by n squared divided by n squared over n squared plus 4 divided by n squared. So what do we get? Let's simplify first. So limit as n goes to infinity, we have 1 over n here, and 1 plus 4 over n squared. So clearly, if you apply the limit, we get 0 over that, which is 0. Okay, so condition 2 is satisfied, right? Is satisfied. Okay, so because of that, then by the alternating series test, the series is convergent. So is convergent. Okay. Now, well, let's see. So we still have to determine whether this thing, so we've shown that this is convergent, but is it, all we've shown in this case, actually I thought we were done, but we're not. We've shown that this series is convergent, but we should now investigate if it is absolutely convergent or not. Okay, so let me add to this. So this is not the end of it. We should next investigate. I will delete this. We should investigate whether this is absolutely convergent or not. Let me grab another blank sheet here. So we still need to investigate that. Well, let me just add here, continued on the next page. Okay. And I will delete that. So we will go to right, so to determine absolute convergence. Now we can use, because absolute convergence involves just looking at the terms Bn's in positive form, we cannot use any of the tests we learned about in section 8.3. So we will use one of the familiar ones from last section is the limit comparison test, right? So we will use that. Okay, so let us have, for limit comparison test, we have to establish AN and BN. So let us take AN as the BNs that we already have here, as that, and we will take our BNs. BNs are up to us to pick, right? We will pick anything, any series that we know whether it diverges or converges. It has, the behavior of this one that we pick has to be known to us. So let me take that. Okay, so this will be the harmonic series basically, which we know it diverges, right? So we know, let me add that. We know that the harmonic series diverges. Okay, so we know the behavior of this. Now by this test, we're going to investigate the behavior of what we have. So the way to do it, let's take the limit of the ratio of AN divided by BN. And this is this test. We're going to apply this. So you can remind yourself or refresh your mind by looking back at section 8.3. So thus, the limit as n goes to infinity of an divided by bn is equal to that. So we have all of this, n divided by n squared plus 4 divided by 1 over n, right? So let us, let's see, so what do we get? We get, let's simplify this complex fraction. So we have limit as n goes to infinity. We have n squared divided by n squared plus 4. And then just like before, let's divide every term here by the highest power of n in the denominator. That would be n squared. And we have n squared divided by n squared divided by n squared plus 4 divided by n squared. Okay, so let us simplify this. So we have 1 divided by 1 plus 4 divided by n squared. Now, if you apply the limit at this point, what will we get? We will get 1, and this is greater than 0. So the series that we picked was the harmonic series, and we know that it diverges, and this quantity being greater than 0, then if the harmonic series diverges by the limit comparison test, and this value being greater than 0, we know that the other series that we were investigating, we were testing, also is divergent, or not, to use the phrase that is more relevant to our problem here, not absolutely convergent. Because when we applied the alternating series test, it was convergent, but we just showed that using the limit comparison test, it is not absolutely convergent. Okay, so let me write that down. Let me, so i.e. not absolutely convergent. So here we have a series that does converge according to the alternating series test, but it does not converge according to the limit comparison test, which tests for absolute convergence. So we have overall then this series is conditionally convergent because it's convergent but not absolutely convergent. Okay, let me make a note of that. Thus, or therefore, or let me say finally, So because the series n minus 1, so this is the alternating series, right? Not that one, but the alternating series is convergent but not absolutely convergent. It is conditionally convergent. And this is the final conclusion here. Like that. Okay. Let us look at another example. So here, we know that the numerator varies between -1 and 1, right? Sine function varies between -1 and 1. So let's make a note of that, because sine of 4n varies between -1 and 1. Then if we take the absolute value of this, it's going to vary from 0 to 1. Okay. So now let's compare this with another. So this being the numerator there, we can compare it with another series that we know how it behaves. Let's compare it with the geometric. Sorry, I was a little bit off the screen there. So let's compare this. So then this, if we know this absolute value divided varies from 0 to 1, then we can write the same. We can write sine of 4n divided by, so absolute value of that we know has to be less than or equal to 1 over 4 to the n, right? We know this quantity varies between 0 and 1, the absolute value of it, right? So that means that this, when this is less, if it's just 1, then it's going to be, it's going to be equal to what we have on the right. But if it's anything between 0 and less than 1, then this is going to be smaller than that. Okay, so now because this is a geometric series, right? So, and with the common ratio being less than 1, right? If you put the, so we can rewrite this as 1 over 4 to n power, right? Either that or that, makes no difference. But writing in this way, you can see it's a geometric sequence or geometric series when we take the sum with common ratio 1 over 4 less than 1. And we know these converge. Any geometric series with common ratio less than 1 converges. So let's make a note of that. So because that, which is that, It's a geometric series with the common ratio r equals absolute value of 1 over 4, which is less than 1. Okay. Because this is true, the geometric series converges. And so at the same time, because we're using the comparison test here, again, the comparison test is what we use in section 8.3. It's applicable here because we're only looking at positive values of this series. And so at the by the comparison test, the series is absolutely convergent. Oops, sorry. I apologize. When I get distracted from the screen, computer screen there, I sometimes I go off the screen. Okay. So this series that we began with is absolutely convergent. Okay. And absolutely convergent is very strong. So it means that this is convergent for any value of n. Whether sine function is going to be negative or positive, it doesn't matter. It's always going to be absolutely convergent for all values of n. So let us take a look at another example. Again, this is one of those examples where we are given these terms and we need to come up with the general term for this series. So we need to simplify this, in other words. Okay, so let us to do that, to write this in a more compact series notation, let us unpack each of these terms first. Okay, so if we do that, what will we get? We will get the series from 1 to infinity. Let's write, since this 2 is 2 times 1, 4 is 2 times 2, 6 is 2 times 3, and so on. So 2 times 1, and then 2 times 2, 2 times 3, right? On and on. And we get 2 times n, right? 2n is 2 times n divided by n factorial. Now, if you take a careful look at these, you get in each term, 2, 4, 6, in each term you have a 2, all the way to the one that is that multiplies itself by n. So we can write these 2's in more compact form as 2 to the n power. Right? So if n equals 1, then we get 2. If for n equals 2, and then we will get 2 times 2, and so on. So we can write this as so if we do that, what will we get? We get, and so that we will get, and so, well, these twos. So these twos, so just the first twos, right? So that's going to give us 2 to the n power, depending on how many terms we're adding. So if n equals 2, then we'll have 2 to the 1 power, 2 to the second power, and so on. So we have, we can summarize that as, for these 2's, we have 2 to the n power, right? For n equals 2, we get this 2 and that 2. 2 times 2, which is 4. Right? For n equals 3, we get 2 cubed, or 8. 2 times 2 times 2, which is 8, and so on. So this term models these first 2's all the way to the nth one. Now, the second value, 1, 2, 3, 4, 5, all the way to the n, that is mimicking the factorial term, right? N factorial is going to model that second numbers, 1 times 2 times 3 times 4 and times n. And of course the denominator is n factorial already. So if we then simplify these, we will get we will get 2 to the n power. Okay, this is clearly a divergent series, right? It's going to get, these terms are going to get bigger and bigger for every subsequent values of n. So because limit of that as n goes to infinity is equal to infinity, and thus we can say that limit of 2 to the n as n goes to infinity is not equal to 0. That's all it matters. It's not equal to 0. So by the test for divergence, we know that that series diverges. So thus, by the test for divergence, the series two to the n diverges. Okay. Which is this is the simplified version of the original series that we had. Okay, so another type of test that we have is the ratio test, and after this we will look at the root test. So the ratio test says that if you take the ratio of an plus 1 divided by an, or every next term take the ratio of every next term by the previous term, and take the absolute value of that, and take the limit of the absolute value of that ratio. If whatever you end up with is less than 1, then the series is absolutely convergent. If that ratio is larger than 1, then it is divergent. And if the ratio is equal to 1, the ratio test is inconclusive. That means it doesn't say, we can't say anything about the series using the ratio test. We got to use some other test. Okay? If the ratio test is equal to 1, then the test is inconclusive, and then we have to use some other test. Okay, so let's take a look at an example of this. So it says determine whether the series is absolutely convergent, conditionally convergent, or divergent. And so let us apply the ratio test. If you feel comfortable with this, you might want to pause the video. If not, maybe follow me on this one, and then the next one you might want to pause the video and do it on your own before you see my solution. Okay, so limit of absolute value of an plus 1 over an as n goes to infinity is equal to so this is minus 2 to n plus 1, right? We're taking that, divided by n plus 1 squared. Just replace n's with n plus 1. That's all I'm doing. And then when you divide it by a of n, this is a of n. Okay, this is our a sub n. When we divide by that, it's going to flip it. It's going to flip this, so it's going to be n squared divided by minus 2 to the n power inside the absolute value. And then we have, what do we have? We have the, is there anything we can do to simplify this? Yes, we can. So notice that minus 2 to the n power and minus 2 to the n power simplify, right? So we are left with minus 2 to first power, which is minus 2, times n squared. So limit as n goes to infinity, and then we have minus 2 times n squared. And then that one, and that one. And then minus 2 to first power is that. And then, of course, n squared stays, and then divided by n plus 1 squared. Inside the absolute value. Right? And then let's remove anything from the absolute value that is has nothing to do with n. That would be minus 2. When we bring it out, it's going to be positive. So then we have from here, we have 2, and then times limit as n goes to infinity of, and we don't need absolute value for n's because n is always positive, right? So, and that expression is always going to be positive. So n squared divided by, and let us expand that, right? Let us expand this to n squared plus 2n plus 1. The reason we want to do this because of the next step, which is divide everything, all the terms, by the highest power of n in the denominator. So we have 2 times limit as n goes to infinity, n squared over n squared over n squared plus 2n divided by n squared plus 1 over n squared. Okay. So we have 1 divided by 1 plus 2 divided by n plus 1 over n squared, right? That's, yeah. So now if you apply the limit, what do we get? Let me not forget that there's a 2 in front here. So we end up with 2 times, and that'll be, these two terms will be 0, this one, we get 1. So the limit will be 1, and this will be equal to 2, which is greater than 1, right? What happens by the ratio test when it's greater than, when the limit of the ratios, absolute value of the ratios is greater than 1? It is divergent. So by the ratio test, the series that over n squared is divergent. Okay. So if you didn't pause the video for this example, please pause it. Pause the video for the next one. And that would be for this one. Okay. Hopefully our answers agree. So I'm going to apply the limit of the ratio again, ratio of the absolute value of those two terms. So limit as n goes to infinity of absolute value of a n plus 1 divided by a sub n is equal to limit as n goes to infinity of, so wherever we have n, just let's replace it with n plus 1. So we have minus 3 to n plus 1 divided by, so 2 times n plus 1 will be 2n plus 2. 2n plus 2 plus 1 is 2n plus 3 factorial. Right? Just substitute for n with n plus 1 and then simplify. And you should get this after you distribute the 2. And then we're dividing this by a sub n, which is that. This is our a sub n. When we divide, it'll let's switch it to multiplication and flip the ratio here. So we have 2n plus 1 factorial divided by minus 3 to n power. Okay. And then let's simplify this. There's always quite a bit that we can simplify when we apply the ratio test. So we have this minus n 3 to the n with that one. So we are left with minus 3 to power 1, which is just minus 3. Times, now something interesting happens here, but let me do it in steps. So if for now, let me keep that. So 2n plus 1 factorial divided by, now let's obtain the first few terms of this. What do we get? We get 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. right? If we get the first couple of terms of this factorial, this is what we get. But the nice thing is now we can, these two factorial terms from numerator and denominator cancel out. We get a much simpler expression. Of course, we're going to bring this out because minus 3 has nothing to do with this limit. So we're just going to put it as a constant in front here, positive constant, and then times the limit as n goes to infinity of 1 divided by, and I didn't even need the absolute value because these two terms are going to be positive. So 2n plus 3, 2n plus 2. Again, the absolute values are not needed at this point. Anyway, so we get 3 times. If you apply the limit, this is certainly going down to 0. 3 times 0, which is 0, and this is less than 1. And we know that when the ratio test leads to a value less than 1, that means the series is absolutely convergent. So by the ratio test, is absolutely convergent. I hope this matches the result that you got when you worked on this on your own. The next test, it's called the root test. So we basically take the root of an usually with this test, you have an expression that has, as a whole, has a power. So you take the root of that expression, taking the index equal to the whatever the power you have. So, or the nth or the nth root of it. Not equal, but let me just say the nth root. So let me take that back. So you just take the nth root of it, the index being nth root of whatever expression you have that has been written to some power of n. So any expression, series expression that has been written to some power of n is a good candidate for this kind of test, for the root test. Take the nth root of it, and if the value, and take the limit of that, and if the value you have is less than 1, then the series is absolutely convergent. If that value is greater than 1, then the series is divergent. And just like the ratio test, if that limit is equal to 1, then the ratio test, the root test is inconclusive, and the test gives no information. So we have to use another test. Okay. So let's go over a couple of examples of this. Here's one. If you want, you might want to pause the video, even though this is the first example, and see how you do. Okay. Maybe our answers agree, maybe not, but it's a good idea for you to pause the video and work this out on your own first. Okay, so we take the limit of the nth root of this. Notice that we have an expression in this series to some power n. So limit as n goes to infinity of nth root of absolute value of an, and this is our an, right, the whole thing. So we have limit as n goes to infinity of, when you do that with this, the powers cancel each other. This nth root with that power cancel each other out, and so we have n squared, we have whatever is left inside the parentheses, over 2n squared plus 1. Okay, and then just like before, we want to divide every term by the highest power of the n that is in the denominator, and that is n squared. Okay, so let's do that. And we have n squared over n squared plus 1 over n squared divided by 2n squared over n squared plus 1 over n squared, right? So simplifying that, we have 1 plus 1 over n squared divided by 2 plus 1 over n squared. And then, of course, apply the limit here, we get 1 over 2. Of course, 1 over 2 is less than 1, which is what some value for less than 1 is what we're looking for when the series is convergent. So we can say that the series is absolutely convergent. So convergence by the root test and the ratio test is automatically absolutely convergent. Okay, or it means absolute convergence by either of those tests. So I hope this is the result you also got, working this out on your own. Here's another one. So for this one, you should definitely pause the video because you've already seen the example. So it would be great if you do that. Okay, so looking at this power of this entire expression, root test would be a natural choice for us here. So solution so the limit as n goes to infinity of the nth root of absolute value of a sub n, and this whole thing is a sub n, so we have limit as n goes to infinity of nth root of 1 plus 1 over n to n squared power. Now if we write this expression in terms of rational exponent, this is what we get. We will get limit as n goes to infinity of 1 plus 1 over n to n squared divided by the index, which is n, right? So if we simplify this, we get an interesting and very familiar result. We get n, right? So what is this? The limit of this expression, 1 plus 1 over n to nth power. So recall from, I guess, calculus 1. So recall that this is just equal to the value e, right? We call that, so we have the limit as n goes to infinity of 1 plus 1 over n to n equals e, right? E, the famous value, irrational value, and that is for sure greater than 1, right? So what does this mean? If the root test results in a value that is greater than 1, then the series is divergent. Okay, I hope this session has been helpful to you. And if not, please bring your questions to me. And for now, have a nice day, and I hope to see you again next time.